Hi, welcome to the Calculus 1 lecture series. And we are in the unit number 2. We'll talk about the derivatives. So in the previous few lectures, we talk about all the derivative formulas and the rules, right? And now we start working on the application part. So in here, in this lecture number 15, we're going to talk about is the exponential growth and decay, and what is that, and how do we solve this type of the problems here. Okay, so let's go ahead to go to our lecture notes and let's start. Okay, so first things, let's take a look. What is the law of the natural growth? Okay, so the natural growth and the decays here. So let's take a look. So we say it's dy dx is equal to the ky. Okay, so this one's here is called the law of natural growth for the k is greater than 0, and we'll say is the law of natural decay if the k for the k is less than 0, right? So the first things here, let's highlight it. So if it's growth, then the k is greater than 0. And if this is decay, then k is less than 0 here. So what exactly, so here, what is exactly this equation tell you? dy dx equal to the ky here. So basically this one's here, it tell you the dy dx is here, right? The way is equal to the ky. Okay, so we know the derivative is rate of the changes, right? So in here you can interpret that is, you say that the rate of the change is, and the case here, in fact, is a constant, right? So you can say the rate of the change, right, is a proportion to the functions here, right? So it's that's why the y's here, right? Take a look at y's here, right? So this is a function. So the rate of change of the y is proportion to what is the values there, right? So now if you take a look, so I want to see what type of the function is a natural growth function or a natural like decay function. So if you solve for these ones here, and then you will find the y functions here, right? So the yt's here is equal to a value, we call this the y0, and this is the EKTs here, okay? So let's take a look to see this is true or not. Okay, so if I take the derivative, okay? If I take the derivative on both sides, okay? So if I take the derivative of both sides, so I will have what? dy dt's here, right? So if you take the derivative of both sides, you will get a dy dt on here. Then what is here? So because this is y0, this is a constant, right? So the y0 is still here. And then the exponential, we know the exponential, the derivative will be itself, right? And then you use the chain rule. So what is the chain rule? Chain rule is k. So that's why you will get it as k times the y0 EKT here. Did you see here? And what is this one here? Y0 EKT is what? Is your original function yt here. See here, so the rate of the change is equal to a constant times the original function, yt is here. That's what we mean here, all right? So that's what we say is the natural growth or is a natural decay. So here, this is the very important functions, right? So that's why the whole, this section is based on the yt is equal to the initial value times the e to the kt. So of course, what is this k? This is the rate of the changes, right? So k is the rate of changes here. And the y0 is what is here? This is the initial value, right? And the t, the reason we use the t, this is the times here. Okay, so this is the yt is equal to the y0 and the ekt. That means that if you take the derivative of both sides, and then it will be, so that's also we call out the, is derived from this, right? So it's the rate of the change is proportion to its original function. That's how do we define it. Okay, so now let's take a look at how do we do few problems here. All right, so now these ones here, they say the initial value is 3. Find the solution for the dy dx is equal to 4y. So we know the solution for the functions here is y, correct? All right, so we know this is the y's here. So we know the yt, right? This is the solution, is y0. So what is the initial is e, correct? And then to the EKT. So where is K here? This is the case, right? So what is the case here? K is 4, right? So I have 3 E4T's here. That's what we mean, how to find the solution. All right, let's take a look. The second one is here. They say if a function yt satisfies y prime equal to -2y, -2, and the graph of the function cross at y-axis. Okay, so this is what I said, the graph cross at the axis is 5. What that means, so when they say cross the y-axis, that means, the function cross here, we say cross here is 5. So what's that mean? That means when x equal to 0, right? So that means it's y equal to 0. So these numbers here is what is our initial values, right? Okay, so now you have here, you have y prime over y equal to the -2. And you can switch that. You say this is y prime equal to the -2y's, correct? Then y prime we know is the dy d what, dy dt or dx is here, right? Is equal to the -2y's here. Okay, so now I know the solution, right? Remember that one we highlighted here is y0 ERTs, right? Okay, so now what is the YTs here? So the YTs here is Y0. Where is Y0? Is 5 EKT. And here, where is the K? Is this number, right? It's a proportion to its original function. So K is -2T. So we know the K here is negative. So what type of the function we have? We have a decay functions here. Okay. All right, now let's take a look at the number 3 here. So all this problem is all based on this formula yt. Let's write here so we can use it. Y0 EKT here. Okay, so now we say the half-life of the radium is approximately 1600 years. What is the mass of a 10 milligram sample of the radium after the 40 years? Okay, so this mass sample, 10 milligram. So this is what? This is my Y0 at what? Is 10 milligrams, right? I start with it. So what means the half-life, right? Okay, I started at, so half-life, that means I only have a half of it left. Okay, so YT is the future values, right? So here we say, okay, half of left, how much you have left is 5, correct? Right, so I have a 5 is left, and I start with 10, then EKT here, right? So how many years? 1600 years. Do I know my K? No, I don't know my K, so I want to find it, right? So this is the EKT. So what is, how many years here? Yes, what, 1600 years, right? So I want to solve for K. So how do I solve for K? I divide by 10 both sides. And so both sides here, so this will be what? 1/2 is equal to E K times 1600. And now you take the natural log both sides, right? So the natural log 1/2 is equal to K 160. So what is your K values? K value is 1/1600 and the natural log 1/2. Am I right? Okay. Now you got this is your K. Now I can substitute to my original function. Y0 is 10 and this is the E. Okay, K is this number, right? It's 1/1600 natural log 1/2, and the whole thing times what? T here. All right. Okay, so now I want to simplify this a little bit here, right? So here, take a look here. So this is the 1/1600 natural log 1/2 times t, right? I just want to take a look at this part. Okay, so now for these ones here, so this one will give you t, the 1600 natural log 1/2. Correct? All right. Now you use the log function properties. I know the log function property, this is the constant. What I can do, I can move to the exponents, right? So that's what is a log function. We talk about that in the pre-cal. So this is a natural log 1/2. So you will have the t over 1600. Okay, now you bring all this is what I highlight in the blue, right? So you bring these ones here, this is the 10, and then this is the E, then this is the natural log 1/2 T 1600, right? Okay, so now, E and the natural log, we find each other. So they are the inverse functions. So now finally, this is my answer is 1/2 and the t to the 1600s here. All right. And the same way, this is the half-life, like for example, like a virus growing, it we call this the double life, right? The double life is the similar like the half-life, it's just a double. Then instead of 1/2, what you put here, you put a 2, right? Your double life, right? Okay, so now they want to ask what happened, you know, if you're at the year 50s, right? So when you come to the year 50 years, how much the things left. So you say, okay, 50s here. So you will have 10, then this is the 1/2. Then you put a 50, 1600. And then you put it into your calculator. You will get this is close to the 9.79 milligram. Okay, so this things seems is very decay, very, very slow, right? Okay, so it's not after 10, 50 years, it still got 9.79. That's why it takes 1600 years to get a half-life, right? Okay, now let's take a look at the number 4. So here another examples here. All right, so this is the bee's colony. All right, so we said a bee, you know, move move its hive to a new location 6 years ago. 3 years ago, there were 400 bees in the new hive, and today there are 600 bees here. Assume exponential population growth. What was the initial bee populations? Okay, and what will be the next years? Okay, so we said, so like in here, so a colony moved to 2 locations 6 years ago. 3 years ago, there were 400 bees here, right? So I said Y3, I have how many? I have 400s, right? So we assume the when they move is t equal to 0. And then today, this is 3 years ago. So today is 3 years ago. So today is how many years? So it's 6 years, right? So the Y6, how many bees I have here? I have 600 bees here, right? So look here, right? Because of a colony of the bee, they moved 6 years ago. So 3 years ago, there were 400 bees. So that means Y3 equal to 400, Y6 equal to 600. Okay, so let's try to write down our formula here again so we can see. So this is YT is equal to the Y0 EKTs, right? Okay, so now let's try to write it and try to solve. Obviously, we need to solve my rate, right? Okay, so in here you say 400 is equal to, right? I don't know what is my initials, right? So I want to find it. So E0, Y0, and the E, and I don't know the K. So I need to try to find my rate. So this is a K. But I do know how many years I get a 300, 400. I get 3 years, right? So it's a 3K. Okay, so now let's take a look. Then at 600, so Y0, use the formula. So still is E, the same K. Now, how many years I get 600s? I have 6 years, right? Okay, so this is my equations. So I have 2 variables, unknown variable, Y0 and K, but I only have 2 equations, okay? So how do I solve it? Okay, so we say, hey, let's do this. How about, so I said that 600 divided by 400, and I know the 600 is Y0 E6K, and this is Y0 E4K, right? Now I solve it, so this is 3/2 is equal, right? So here, this one is Y0, Y0. So how many Ks here? Here is 3, not a 4K, it's 3Ks, right? So I get E to the 3K. So how do I solve for K? I take the natural log of both sides. So I have a natural log to 3/2, right? I have a natural log of 3/2 is equal to 3K, right? Okay, so what is the K's here? So K is 3, the natural log of 3 what? Natural log of 3/2 here, right? So natural log of 3/2 over 1/3, right? So now we said, okay, I want to find the, now the remaining, I want to find the Y0s here. I can use this equation. I can say 400 is equal to the Y0. Then E, my K is 3, the natural log of 3/2 times 3, right? That's pretty good. So this is a times 3 here. Okay, so 3 cancel, and the 3 cancels here. Is good. Also, the natural log and the E, they are what? The inverse function, they cancels here, right? So they become 1s here. So now I have what? I have 400 is equal to the Y0 times what is 3/2. So what is the y0? What is the initial? How many b's I have? I have a 400. This is over 3/2 here, right? So I have about 267 b's to start with, all right? Okay, so I have, the 267 b's to start with, and they say, what is the next year? So they moved 6 years ago. So next year, what is the year? It's year 7, right? So that means it's year 7. Okay, so for year 7, I use this formula again. So y0 is 267 times the e. And what is the k? K is 3 natural log 3/2, then times what? Times 7 here, right? Then you can put it into your calculator and you will get a close number about 688. Okay, so this is how do you solve. They give you a 2, the 2 times, right? Okay, so now let's take a look at number 5. See here. They said number 5, they said 1 hour after bacterial culture was started will be 300, and then after 2 hours, right? So after 2 hours, it going from the start will be 900 here, right? Okay, so 1 hour, so this is 1 hour is 300, and 2 hours is 900. So I want to find how many of them after 4 hours after start. Okay, so here is the same. 1 hour, so I know the y1 is equal to what? 300. So 300 is equal to y0 and the e, what e here? K times 1, right? Okay, so good. And then now I also say 2 hours, so it's y2 is equal to how many? 900 is equal to, okay, so the 900, okay, so the 900 is equal to what? Y0 E, right? So what is the K here? So this is the K, and how many hours? 2 hours, right? So I want to solve for K, and I want to solve for the initial. So this one is easy. Also, I can do a ratio. I would say it's 900 over 300. So the 900 here is y0 e2k. 300 here is y0 ek here, right? Okay, so now here, this is 3 is equal to boom, boom. This cancel. How many ek here? I have 1 ek, right? So what is the k? K is equal to the natural log of what? Natural log of 3 here. And then you can plug the k into the one of the equations. So I use this one, doesn't matter, you can use the other one. So you say 300 is equal to the y0 e. What is the k? Natural log of 3. That's pretty cool, right? So then this ones here is inverse functions to each other. So that's why we said 300 is equal to y0 times 3, right? So how many y0s here? So y0 is equal to the 300 divided by 3. So what is my initial value? My initial value is 100. And now they ask you how many after 4 hours, right? Okay, so I just plug in this formula. I said y4, right? 4 hours is equal to y0. What is y0? Is 100. And the e, k is natural log of 3. How many hours? 4 hours, right? So This one's here, be careful, you want to simplify this, you don't really need a calculator. So this is a natural log of 3. This is the constants you can move to here. After you move the inside, then this is what? This is the inverse functions, right? Okay, so this is the inverse function. I should include the 3. So this is the inverse function, so they become 1. So this will be equal to 100 times the 3 to the 4th, right? So that means after the 4 hours, I'm going to have 81 hundredths here. Okay, so this is the same problems here, right? Let's take a look at one more. So then we will be very good at it, okay? So, and so here they say this samples here has an initial mass is 90 milligram. After 100 days, 60 milligrams left. After 100 days, 60 milligrams left. Assume natural decays here. How many days until this sample only have 20 milligram? Okay, so let's see here, the initial. All right, so I can know that this one is Y0 is what? It's 90, right? Then they say at the T 100, so it's Y100. And how many I have here is 60s, right? Okay, so now I know the 60 is equal to F0, so it's 90 times the E. Do I know K? No, I don't know K here, so it's a K here. And what is how many days? It's 100 days. Okay, that? Okay, now let's try to solve it. So I divide by 90 over. So this is 2 over 3 is equal to the E 100K here. All right, so this is a 100K. So now I take the natural log of both sides. So this is natural log of 2/3 is equal to 100K here, right? So the K, so what is the case here? So K is equal to 100 natural log of 2/3, right? This is my K, good. Now let's say, I want to see how many days I'm only going to have 20 milligram of the mass left. So I will say it's 20 is equal to what? 20, all right? So the 20 initial is 90, right? So it's 90, and the E, what is the K here? K here is 100, and the natural log of 2/3. What I'm looking for? I'm looking for T's, right? How many days? Okay, just like before, we can simplify this a little bit. I'm going to highlight it here in this color. And let's see, we can simplify that. So this is the 100 natural log 2/3 times T. So really is 100T times natural log 2/3, right? And then this is the constant based on the natural log. What can we do? I can move to the inside. I can move to the inside and become what? Will become, right? So the name, this is natural log 2/3 here. And then this will be the T 100ths here. Now I put this back. Okay, so take a look here. I move this back. So this is 90 and this is E. So this is a natural log 2/3 to the T, the 100ths, right? So just like we did the half-life. So here, these two, they are the inverse functions, so it's a cancel, right? So then I will have 20 is equal to 90, 2/3 T over 100. You divide it by 90, both sides is 2 over 9 is equal to the 2/3 T over 100ths, right? So how do you solve this one? You say, hey, I can take the I can take the natural log of both sides, right? So I will take the natural log of both sides. So this is natural log of 2/9 is equal to the t over 100 times the natural log of 2/3, right? Okay, so what is my t going to be? So if you move this 100 times 100 both sides to here, right? So then your t is going to be equal to natural log 2/3, and this is 100 times the natural log 2/9. Whoa, yes. So you can put it into the calculator and you will see it's about 331 days, all right? So according to this rate, it's about 371 days, the mass will drop to the 20 milligrams here, okay? So it's pretty easy sections, right, lecture. So the whole thing is based on the Y0, I'm sorry, it's YTs, right? So based on this equation, right, we use it many times here. So that means YT is equal to the Y0 EKT, right? So don't forget that. Okay, so we're going to stop our first videos here. And then the second video, we're going to talk about applications, the similar, like we're going to take a look at how do we calculate interest, all right? So how do we compounding the interest here? Okay, that's it. Okay, let's talk to you next time. Okay, bye.